All right. Hello, everyone. Hope everyone is doing well. Let me know if you can hear me or if you can't hear me, if there are any issues with the audio. Um, Welcome, everyone. So today I wanted to talk a little bit more about chaos theory because, I guess last time I also talked a little bit about chaos theory. And today I wanted to do a type of simulation called a billiard simulation, okay? It's where you take a bunch of particles or like billiard balls and you just like rattle them around a table. So let me show you some of the videos that I've made here. I just need to find them. So let's see here. This would be, well, I need to make sure I mute it. Okay. Pause, reverse. Okay, so what is this exactly? So hello, Manoj. How are you? Let's see. Okay. So this is a million particles. Okay, actually a million particles, and I'm gonna let them loose at some trajectory inside the circle. Okay, let's see what happens. Now it's quite pretty, I think. Okay, so it's really quite beautiful, and what's interesting about this is that this is actually not chaotic. So what exactly would make something like this chaotic? You know, you would want there to be mixing, you know. Thank you. I've been putting more work into them, you know. Well, I've been trying to edit them more so that people can consume them in bite-sized chunks. So in any case, so this is a million particles, and this particular simulation is not chaotic. Now, what exactly is it that makes something chaotic? Well, if you notice, these particles, and they're just reflecting like usual reflection rules. So the angle of incidence is equal to the angle of reflection, or whatever it's called. And they're going around a circle, and you notice they remain in some kind of pattern, right? They don't like mush all over the circle. Also, it feels like if you took a bunch of particles close together, like if you take a bunch of particles that start close together, they stay together, and it seems like there may be parts of the circle that like don't get visited as often. These are all things that you would not want for a chaotic simulation. Now, one of the things I tried, I'm not really sure how well it went, is I tried to add sound to these simulations. So if we rewind here, I'll actually unmute it so you can hear it. Okay, so I took like a lightsaber sound effect. Let me see if I can find the sound effect that I used. Let's see here. I just need to find it on my computer. So I started with a lightsaber sound effect that I have now unfortunately lost. Oh well. And then I sped it up twice, and basically that sound is going to play every time any one of these particles strikes the boundary. Okay. Hopefully the audio comes through. Let's see what it sounds like. It's interesting, right? And then you'll see collisions here again. It's very, very interesting. I might let this run through, and you can see this simulation finish up. So, personally, I think this is quite beautiful. I also wanted to spend some time talking about exactly how you get. So you might think this is a lot of like code to get like a million points, and you'd be right. You have to make some compromises. You have to introduce a significant number of efficiencies in order to do this many points inside an object. And if you're curious about time, I did this in Python. I did this all in Python, and it only took about like 9 minutes to render all of these frames. So this is a 5-minute animation, and so that's 300 frames. I'm gonna mute it now because the sound is getting a little annoying. But this is not. Wait, hold on. So this is 9,000 frames, I think, and that should amount for to about 5 minutes of animation, and it was able to produce all of these frames in, like I said, about 9 minutes. So not quite enough for me to do it in real time, but enough to get this this setup going. So there's that. And what I like about my approach is that you can do basically any number of points, and you can also do any shape as well. So you can do you can have the particles reflect around basically any shape. The caveat is you need to know a good implicit equation for that shape. Okay, so circle has a nice implicit equation. It's just x squared plus y squared equals 1. You need to have a nice implicit equation for the shape, and then you can reflect your million particles around the shape. So where do the clusters on the line come from? Floating point errors or some such? I am not 100% sure. I'll show you another one that I did. Let's see here. So this is a group of points inside an ellipse. Where'd it go? Ellipse animation. So, okay. This is a group of circular points inside an ellipse. I don't think you'll get bands as bad here as you do there. But my suspicion about where the bands are coming from, hold on, let me write while let me try and do good screen management. Okay, so my suspicion about where these bands are coming from is essentially, as you say, rounding errors. So for every point, I update it by some velocity. And in an effort to get these animations to produce quickly, right, to not take too long, I set the velocity to be relatively high. So the points like jump a lot. And then, so in my methodology, right, like if this is the boundary, the jump might take it over the boundary, and then it might reflect after the boundary. So my feeling is that the reason I'm getting these is because I set my velocity too high, because I just wanted to produce as many animations as possible for this video. Maybe for the edit later on, I'll do one where I set the velocity to be very, very low, and then I'll speed it up later, and then you won't get these this like banding effect. So you see it less in this simulation over here, but you can still see them. You can still see bands a little bit. Yeah. So, okay. So I wanted to spend some time while this plays in the background, just because it's very pretty, right? I wanted to spend some time just, I wish there was some way to like pin this to the top of the screen. Like no matter what I do, it doesn't go away or stop playing. Oh, I could do it in OBS, but oh well, I'm just not gonna mess with it. So I'm just gonna zoom this down. So this forms a nice bit of backdrop over here, and then I'm gonna just take my paint document here, expand that downward, expand it rightward. Okay, this is my frame. So how exactly is it that I was able to do all of these computations? Well, here's the idea. Here's the master plan. So you start with an equation that you start with a curve that you know an implicit equation of, right? So in this case, for an ellipse, it's like x squared over a squared plus y squared over b squared equals 1. I'm sure you remember this from your from your pre-calculus days, or whenever you took that class. So this is an implicit equation for an ellipse. Okay. Now, normally what you would do is, let's say you have some curve, right, C, and you would like to have a moving particle reflect across the curve, right? So you have some particle, it like goes here. You would have to compute the tangent line to this curve, right? Maybe the tangent line looks something like this. And then you would have to compute the angle of incidence, right? And then set that equal to the angle of reflection, right? And of course you would have to do this for every single point. But because there are a million points over here, as you can imagine, that's a lot of logic to do for each and every single point. What we really want in this situation is some function we can apply to all of the points simultaneously, some like fast moving function that does not have any like if statements or anything like that in it, that will automatically perform all of the reflections of these 1 million points that we need / desire. Okay, so how are we going to do this? So here's my idea. I'm quite happy with this. I think it turned out very well. There are a few floating point errors here, but I do think that if I set the velocity to be higher, they would in fact go away. So what is how did I do this? Well, notice that if you were to do a contour plot of this equation, like x squared, so I think I did 2x squared plus 3y squared for this particular ellipse. I think it was 2x squared plus 3y squared equals 6 for this particular ellipse. Now you might notice that if you do like 2x squared plus 3y squared equals 5, you'll get like, a different ellipse. And if you do 2x squared plus 3y squared equals 4, you get a different ellipse. Or if you do 2x squared plus 3y squared equals 7, you'll get a different ellipse still. If you were to plot all of these together, you would get what's called a contour plot for this equation. So let me just show you the contour plot for this equation. Let's see here. So here. Okay, so let's just do a quick contour plot. So you just do contour plot of this equation is, let's see here, let's keep it. Oh, okay, I can play another one in the background actually. I did a second ellipse. Let me show you another one that I did. This is another ellipse that I did, but this one, I started with like a smaller packet of particles in this one, so you can see there. I guess it's nice to always have something entertaining running in the background in case you don't want to hear about the math. But if you do a contour plot of this equation, right, you do like, what is it, 2x squared plus 3y squared. And let's say x goes from -2 to 2, y goes from -2 to 2, right? This is what the contour plot looks like. So this is what the curve looks like if you set 2x squared plus 3y squared equal to 2. This is what the curve looks like if you set it equal to 4. This is what it looks like if you set it equal to 6. And this is what it looks like if you set it equal to 8, and so on and so on and so forth. So you get different ellipses, okay? So my master plan is for any point on the plane. So let's say you pick this ellipse to be special. So you pick this ellipse is the one that I want to reflect across. Then you can evaluate this function at any point, and it'll basically tell you the distance. Or it's not really a distance, right? But it's acting as a proxy for the distance. So essentially, I know that any particular point is going to be really close to the ellipse if 2x squared plus 3y squared on that point evaluates really close to 6, right? You see that? So if it's evaluating like 5.9 or something, I know I'm getting close. And if it evaluates to 6.1, I know I went over. So instead of computing distances, I thought that if I use implicitly defined curves, curves that have equations like this, I can essentially use that as a proxy for my distance. And if I use this as a proxy for my distance, I don't need to compute the distance for all 1 million points. And I can have nice, smoothly running animations, as you see over here. Okay, well, once again, keep in mind this is not a distance, right? But I'm essentially computing 2x squared plus 3y squared at any point. And the idea is that if 6 is my special ellipse, right? If 2x squared plus 3y squared equals 6 is my special ellipse, then I know if 2x squared plus 3y squared evaluates to more than 6, then I must have gone over. Then I must be on the outside of the ellipse. Make sense? That's how I'm setting this up. All right. That is one part of the struggle, right? The other part of the struggle is reflecting your points, right? The other part of the struggle is, you want to take a point over here and you want to reflect it across, right? So that involves computing tangent curves and so on and so forth, which is, it's a pain. You would have to do it at every point. But it turns out you actually do not have to do it at every point. If you compute what's called the gradient for this equation, So you have 2x squared plus 3y squared. You differentiate it with respect to x, and you differentiate it with respect to y. So if you differentiate this equation with respect to x, you'll get 4x. And if you differentiate this equation with respect to y, you'll get 6y. So I'm going to pay attention to this vector, 4x comma 6y. It turns out that this vector will always be perpendicular to the ellipse. So for example, if this is my ellipse, right, and this is my point xy, if I compute 4x comma 3y, that will always be normal to the ellipse. So I can get a hold of the normal vector on this ellipse, which is really nice because if I have a normal vector, I can essentially do the math to reflect across this normal vector. Okay? And again, the nice thing about this approach is that you can essentially do this for any implicit equation, and then you can use it to reflect across, right? So the fact that you can do this for any implicit equation, you can compute the gradient. The gradient will give you the normal vector at any point, right? And then you can use the normal vector to reflect across. So there's a little bit of math that you need to do in order to figure out how to reflect across. Okay, so for example, let's say this is my vector. Okay, let's say this is my vector. Let's say I've computed the normal vector to the curve. So I have like this. This is my normal vector over here. I would like to compute this vector, the one that points this way. Now let me draw all of these vectors originating from the same point as you usually do with vectors. So let's say this is v, and this is n, and I'm trying to reflect v across n. I'll just play it one more time. It's fun. So I'm trying to reflect, I have more, but I just want to finish this conversation before I get into chaotic dynamics and all of that stuff. Okay, so I'm going to draw these vectors all originating at the same point. Okay. Okay. This is going to be my v, and like I said, I want a reflection of v like that, so it leaves out there. All right. How do I do this? Well, first and foremost, I can get the projection of v onto n, which is like the vector parallel to n that's as close as possible to v. That has an equation. You learn it in, like your multivariable calculus class. It's going to be v dot n over n dot n, n. So that's going to be our p. I'm going to call this p, okay? All right. If that's p, then this green vector over here is going to be v minus p. Okay. So this green vector is going to be v minus p. As usual, I'm going to draw my vectors starting at the origin. So this is going to be v minus p. But now notice that if you do, so this is, okay, yeah. So this is v minus p. And also, let me draw over here. This one pointing this way is negative p. You see that? So the vector I'm after, that's this vector over here, is the sum of v minus p and minus p. So the vector that I'm after is just v minus 2p. Very simple, right? So if you have access to an implicit equation for your curve, you can come up with a normal vector, right? And if you have a normal vector, it's very easy to come up with the equation for how to reflect across in this situation, all right? All right. Now we get to the next problem that you really don't want to solve for 1,000,000 points, which is, where do you need to compute the normal vector? Hello, Mohammed. How are you? So now we enter the next problem, and please, anyone, let me know if you have any questions. Now we enter the next problem, which is, how do you compute the normal vector, right? So I mean, I'm sorry, we know how to compute the normal vector, but the question is, where do we compute the normal vector? So let's say you have a point, right? And the point, if you incremented the velocity, would wind up out here, all right? Then you would have to, for this point, so you would have to think about where it would intersect, right? which is this blue point, right? So you have to think about where it would intersect this blue point, and then at that blue point, you would have to compute the normal. And then if this vector is a v, you would get this outward pointing vector as a v minus 2p, right? Where I talked about how to get p. This is really difficult. I mean, this is very time consuming to do for 1,000,000 points. So my hack was to just, instead of doing v minus 2p over here, I just computed the normal vector over here, and I just reflected across this point over here. Okay, so it's off by a little bit, and you can see it be off by a little bit, right? So you can see these little like bands appearing over here, right? So this is a result of my decision to not go for the point, not reflect across the exact point, but to reflect the point right before it hits, and this causes a series of like very tiny issues, but you know, it's not so bad. You can basically see the behavior of the points, and you know what, I think it's still pretty beautiful. So that was my compromise, but as a result of that compromise, I was able to get the code to run very, very fast. You know, maybe there's like a quick way to do this as well. I didn't really have the time to come up with it. Maybe one of you geniuses will figure it out for me and get this running even faster. Okay. So that's how I was able to figure out what was going on with 1,000,000 points, which is very nice. But now we have another issue, which is if you have 1,000,000 points, right? If you have the XY coordinates of 1,000,000 points, how exactly do you graph that? I mean, it might seem like nothing. Like, you know, graphing like 100 points or graphing 1,000 points or even graphing 10,000 points is like nothing. But graphing 1,000,000 points is a lot of work because you need to take every single location, right, and plot it on an image. You need to do that 1,000,000 times, right? So what is the quick way to do this? Well, it turns out the quickest way to do this is to employ like your graphics card if you can. Just look in every patch, see how many points wind up in each patch. This is a highly parallelizable operation. You do need to write a lot of code for it. Luckily, someone else has already solved this problem, so I did not need to solve this problem. So I used a Python library called Datashader in order to get this done. So I used a Python library called Datashader. What it does is exactly what I've said, is it divides your image into patches, and in parallel, it figures out how many points wind up in each patch, and it produces like a rasterized image that you can just display. You can't zoom into it, of course, because it just produces an image, but it does so very, very quickly by utilizing the hardware on your computer in the best way possible. So in any case, that's what I did, and I got some code. I also, as those of you who joined a bit early saw, I added noises sometimes to when the points like hit the screen. So not hit the screen, like hit the boundary. So for example, for the one that I just showed you, I guess maybe I'm like getting old, but you know, like Homer Simpson says like "dow" when he stubs his toe or something, you know, bad happens in his life. Let me see if I can't find that particular sound effect. So let's see here. Let's see. Users. Okay, so this is the sound that I was playing with. Get.
No!
Can you hear that?
No!
So I thought it'd be funny if it
No!
played like that 1,000,000 times every time the point collided. And this is what it sounds like. And don't worry, it sounds horrible. I won't play it for too long, but I just thought it'd be funny. Let me find that file one more time. Let's see. So you're about to hear the joy of like 1,000,000 does superimposed on each other. So let's see here. It was this one. Let's see. All right, let me unmute this. Oh, no, okay. It's about to make the collision. Hope you're all ready. Spooky. I don't know. I don't know why. I just found this very amusing. There it is, people. 1 million dose. I hope I hope this is worth your time on this fine Wednesday afternoon. Okay, I'll do one more collision and then I'll stop. I know. Okay. You have understood my secret meaning, Gus. Thank you. Okay. I'm going to stop this now. This is really stupid, but I had a great time with it. Okay. Enough with the sound. Though, actually, if any of you have any suggestions for sounds, like I said, it takes maybe 10 minutes to get 5 minutes worth of frames and then another 5 minutes to render the sound. But we could just do like 1,000 frames. But I do have the code set up where you can set up any kind of like, well, almost any shape that you have an implicit equation for, and any sound it will do this for you, which is a lot of fun. So, okay, now I want to get to like the real topic of this video, which is I actually want to talk about chaotic dynamics. So I said that this one is not chaotic, and the reason this is not chaotic is that these points, they don't wind up everywhere, right? Also, if I take a small cluster of points, they basically stick together, right? It turns out this is a very useful theory to know and understand. It governs how light spreads in a room or how sound can spread in a room, right? And some rooms will not be chaotic like this. It turns out the rooms that are not chaotic are basically circles/ellipses. Everything else is going to be chaotic. So let me show you what I mean. We'll do a side-by-side. Let's see here. Hold on, I want to do... two side by side. Oh man, I don't know if okay, I hope this is possible. Let's see here. I'll show you what I'm up to. I'm just trying to get everything set up. I have this in Premiere, which I can use to like scrub things, which is nice. So what I'll do is I'll shrink this one and put it to the left, and I'll shrink this one and put it to the... Ooh, I'm sorry, I'm messing up. Okay, let me nest this. Let me nest this. Okay, now let me superimpose them. And now let me shrink this one. And no spoilers. I'm gonna shrink this one, I'm gonna push it to the left. And then I'm gonna shrink this one and push it to the right. What happened to my background? I'm not really sure why this background only shows up on the... There it is. Just need to push it to the correct frame. Okay. I've made it too small. Get a little bigger. Okay. They're kind of like interfering with each other. I can do this, I swear. So I'm going to put this one down here. And maybe I'll put them top and bottom. Yeah, that's not the worst idea. So this is the bottom one. And this is the top one. Okay. All right. So as you can see here, I've only made a small change to... let's see. Let's go to the color audio. Okay, I can make this window a little bit bigger. Okay. as you can see here, I have only made a, also let me move this to the left. All right. I have only made a very small change to this. Instead of an ellipse, we have ourselves an egg, okay? An egg is a lot like an ellipse. I just happen to know the implicit equations for an egg, which means I can run the simulation on it. And you will see that, and I'm gonna let loose the same donut set of particles at the same time, at the same speeds, and you will see how look at the title of the video, how a simple change can create chaos. Chaos, yes, okay, let's go. So we go here. I'll fast forward too. Maybe I should have played them both at twice the speed. Oh my goodness. You know what would have been smart? If I changed the other one like imperceptibly. Like if I changed it like if it was really close to an ellipse, but I only changed it in a way where okay, you know what? This is a little slow. I might speed them both up. Just give me 1 second. Let's play them both at about 250% of their normal speed. More spoilers. Okay. Okay, so now this ordeal should be over in about 3 minutes. All right, let's see what happens. Hopefully you can all see. All right. All right. Goes up. Yeah, you know, it looks like the egg one is holding together fairly well. But, uh-oh, what's going on here? That's right. So as you can see very quickly, and you know, you can ignore my like weird rounding errors, but you can see very quickly that the egg is showing a bit of chaos. You see that? So the dots in the ellipse are staying together, right? But the dots in, or at least dots that start together stay together, I guess is what I'm trying to say in the ellipse. But in the egg, dots that are starting together are not, in fact, staying together, right? Parabolas aren't chaotic as well. So I'm talking about closed shapes, Mohammed. So hopefully that answers your question. So I'm only referring to shapes that are closed. You wouldn't really be able to tell if a parabola is chaotic because wouldn't the points just eventually like bounce away over time? So I do think you need a closed room. But I do agree that if you like launch a bunch of points in a parabola from like the sky and you like push them down, they will all like go to the focus, right? That's like the big thing about parabolas. So in any case, I hope that answers your question, Mohammed. All right. Oh yeah, I ran out of frames for the other one, but you can still see the chaos proceed with this bottom one over here. And over time, it will. Oh, actually, I realize you guys can't see this. Over time, this will actually fill up the entire egg. And you know what? I think it's quite beautiful. So I think one thing that I'm going to do after I'm done streaming is I'm going to redo some of these animations, which with a much lower like V value, and let them run for like a couple of hours. And also what I might do is increase the resolution dramatically. And in doing so, it'll get rid of weird rounding artifacts, for one. And also, you'll be able to see the beautiful patterns that emerge, I think, a little bit more clearly. Actually, it might not be the worst idea to like get it started right now. But yeah, so as you can see, basically all of the points are spreading quite rapidly through this egg. Okay, so there you have it, people. I might look up. Oh, by the way, if you guys have any ideas for sounds or shapes that you would like to see this evolve in, please let me know. I can definitely include it in the edit, though it might take too long for me to include it in the actual video, like in the actual stream at the moment. But if you guys have any interesting ideas for shapes or sounds, I would love to try it out. So one of the ideas that I had was a heart, actually, but the problem is the implicit equation for a heart is not well behaved. So let's see if I still have it. So let's see. Just look up the implicit equation for a heart. Yeah, so it turns out if you would like to graph a heart, let me copy this. This is the implicit equation, right? So if you just do a contour plot, also let me zoom in a bit. Okay, so if you do a contour plot of this equation, where let's say x -2 to 2, y -2 to 2. I don't know why this isn't working. Huh. It's being weird. Let's see. -5 to 5, -5. That's very odd. Maybe, so I just copied this from online. Maybe the issue is. Okay, I tried this before and it definitely worked. So let me just think this through. So, I don't know. It might be some weird formatting issue from online. Let's see. So let's go x squared plus y squared minus 1 cubed minus x squared y cubed. Okay, I don't know why it didn't work last time, but it worked this time. But as you can see, this is an implicit equation for a heart. So it would be very nice if we could use this methodology on this heart, but the problem is this equation is actually not that well behaved. So just go -2 to 2, -2 to 2. So the problem is, for example, if you plot this contour at 0, like if you set this equation equal to 0, you get a heart, but if you set it equal to like 0.1, it doesn't look like a heart anymore. So my little trick of like using the nearby reflections would not work on this shape. So you would have to come up with like a good implicit equation for a heart. This one's kind of neat, actually. It looks like a heart is melting or something. I don't know. But yeah, as you can see, it just behaves worse and worse. Like you want a contour plot which nearby still looks like the same thing. And the egg had that property, but the heart does not have that property. So you cannot use this exact equation for a heart to do this. However, I think there are other interesting implicit equations out there. Let me look up some. Let's see. Let's see here. No, I feel like the heart is pretty good. You know, I really thought that The Batman equation? I don't think that that one is implicit, Muhammad. I think that that one's parametric, but I can look it up. Let's see. Yeah, that's like a piecewise. So it's like they super glued together a bunch of different plots of a bunch of different things. You would need an implicit equation to make it work. So let's see. Well, okay. You can use any equation, but to make it work quickly, using my method, you would need an implicit equation. So, or you would need some equation where you know what the normal curves were. Let's see. So, ooh, I have some good ones actually. Let's see here. Who says that the room can't have holes? Huh? So, how about? Okay. So I found this interesting article on Stack Overflow, and we can use, I think, some of these surfaces to define something interesting here. So let's see, actually. How is this defined? So BCN is TNX plus TNY plus TNZ equals 0. TN is this. Okay, let me... This is very interesting. So this is BC3. Okay, maybe we can do something interesting with... So BC1, BC2, this is BC3. Maybe we can do something interesting with BC4. So let's see here. So, let's close that. Just define this equation. So let's say TN x is equal to the sum of binomial. Let's see, it's n choose 2k times x squared minus 1 to the kth power, and then x raised to the n minus 2kth power. All right. And then we have, let's see, k goes from 0 to the floor of n over 2. Just make sure everything is good. Okay, let's try it out. So for example, if I do T4x, I get, okay, it works. I get that. All right. So let's try it. Let's see if we get the same thing that they got. So contour plot 3D, T4x plus T4y plus T4z, set that equal to 0. I'm not sure what the x, y, and the z range was for their plots, but we can do x. Let's try -5 to 5. Y, -5 to 5. And then finally z, -5 to 5. Hey, what do you know? Look at that. That's pretty, right? Okay. So that's good. Let's go -2 to 2. Very interesting. All right. So now we can slice this. We can take like a slice of this equation, right? So how do we take a slice of this equation? Well, what I'll do is to take a slice of this, we need to fix a z value. So what I'll do is maybe I'll set z to be 1. Zero to the 0 encountered. Okay, it's looking good. We're getting some interesting shaped rooms. So let's go with equals maybe 50. No, that didn't work. But 100 we know works. What about 90? I really wanted a room with a hole in it, but it doesn't seem to work. You do get it with the 3D plot, but you don't get with the 2D plot. Let's see. What happens if you do like 95? You know, I really suspected that... Oh, sorry. Thank you, Ken. Let's see. So I really suspected that setting Z to be a number would give me an interesting 2D contour plot. I'm still not 100% sure why that did not happen. Because there are points on this curve where... Actually, hold on. Let's go negative 1 to 1, 2 to 1, 2 to 1, 1 to 1. Okay. Yeah, so 1... Okay, so if I take a slice of this curve at, let's say, 1.5, I know something interesting has to happen. You don't get the internal one for some reason. Let's see here. So why don't I set this to 0? Let's see. I'm not really sure why. Let's just do this. 1.5 do 1. Let's do 0.5. Okay, what's this one? 0. Ooh, okay. 0.5 works. Okay, now we have a room with a hole. Yeah, I thought it should. I don't know why it wasn't working, Petros. But there you go. Now we have a slice with a hole. Yay. All right. So now, in order to use the method to... hello, Hitoshi. How are you? Thank you so much for coming. Late or not, I always appreciate it. Okay, so now we have a room with a hole. And so if I'm right, we can use the method to bounce a million points in a room of this shape. First thing I'm going to do is I'm going to increase the size of the room. Over 2. Okay, I increased it too much, so over 1.5. Okay, that is a lovely room. I'm guessing the normals will point in the correct direction. Okay, now we get to the really annoying part, which is we need to copy this into Python. Because I did everything in Python for this video. But let's see what this equation is. Okay, hold on, let me see. Okay, you know what? That's not so bad. I'm just gonna take this equation, and I'm going to, of course, copy it into Python. Where is Python? My goodness, tell me I didn't close my my Jupyter notebook. It says I have not. It's okay. I can hopefully restart it. Can I restart it? Okay, it shut down. All right, let me open that. All right, it's here. All right, so now, all right, this is my hideous code that I use to generate everything. Okay. So if this works, I should be able to enter any level set, any normal, and well, the normal for that level set, and it ought to work. So let's enter the level set equation. I'm just going to copy this in. Okay. We need to do times 2. I know it's slightly faster to just multiply multiple times, but I'm just going to do that. Okay. Now we need to compute the normals for this curve. So I'm just going back in here. I just need to take this and differentiate it with respect to x. Copy that in. It's going to be a miracle if and when this works. Okay. So this is to the third power. And then I differentiate it with respect to y, and I copy that in, right? Differentiate with respect to y. Okay, get this. Curiously similar. Okay. Okay, what was the boundary value for this one? This is, okay, it's equal to 0. So boundary value is 0. Okay, yikes. All right. Just to double, triple, quadruple check everything, I'm going to copy this function in to here and make sure I get the same contour plot. I do. All right. Okay, assuming I've copied everything correctly, everything should work. Let me make a new folder in which to put the new frames. So I'm just going to make a new folder. Let's see. I'll call this hole for room with a hole. And then, all right, guys, here goes nothing. So I need to make sure it exports to that one. Okay, so enter. Invalid syntax. What did I do? Oh, I forgot you need to put little multiplication symbols everywhere. Okay. All right. Okay, that worked. All right. Now we need to make sure our initial points are all inside the shape. I'm kind of worried that they will not be. Let's take a very tight cluster of points that are centered. So let's see. Let's take a very tight cluster of points, like point 1 is, okay. I'm just gonna see what happens. Hopefully it's defined. All right, do that. All right, well, I'll only do 1,000 frames because I don't want to wait for 9,000 frames to compute. I'll show you the folder as it goes. Okay, let's see what's happening here. I'm worried that this cluster started in the hole, so which is not going to be good for us. Yeah, it started. It's okay. So I just need to interrupt this code. And I need to move my starting cluster of points so that I'm within this region, right? I don't want to be inside this region. I want to be inside that region. So it's looking like if I start my points like in a tight cluster around 1, 1, I should be within the zone. So let's see here. Plus, so let's see, this is a, so I just need to add like 1, 1 to all my points. Doing some more broadcasting. So I talked about it last time. All right. Let's see if that hopefully worked. Okay. I think I'm in the zone now, right? Okay, now it's just computing everything. It's going to take Okay, it's fast, but it's not fast enough to compute everything in real time. So, but I have to say it's looking like it's working. Let me get this ready for prime time because I don't have the code set up so that Python will show the boundaries. I only have it set up so it'll show the points. So let's see here, contour plot. Just need to copy the settings. Of this contour plot. So I'm gonna bounce 1,000,000 points in a room that's shaped like this. That's the plan, Ken. So hopefully that makes sense. I'll show you the video that I opened with. Let's see here. So for example, you can watch this one. So it's like 1,000,000 points, and they bounce around the room. And we're trying to see like chaotic dynamics versus non-chaotic dynamics. So, and the name of the game is like, how do you efficiently get 1,000,000 points to bounce around? That's so that's one part of it, and then the other part of it is just like I said, observing like chaotic dynamics versus non-chaotic dynamics. So hopefully that answers your question, Ken. All right, what was I doing? So I'm trying to export an image of my contour plot so I can superimpose it on these images. Let's see here. Okay, so I'm just exporting the background image. I think it's bouncing around accurately though. Also, I think we're going to observe chaotic dynamics too. It's working, guys. It's working. It's working. It's working. It's working. It's working. Haha. So now, okay. What am I doing? Brain work. Okay. All I need to do is get my background image. So, whole back. All right. And then this. Need to paste in my other contour plot. Put that in. Okay, and then hit enter. Okay, now I have that, and I think all my my 1,000 frames are done. Okay, guys, proof of concept. So I'm gonna open Premiere again. Zoom this in. All right, hopefully you can see this. I'm gonna push these away because I'm not interested in them right now. I'm going to import all of these frames. Okay, sorry, this one's a little shorter because I only printed 1,000 frames. Gus says, have you considered a Discord for this channel? No, actually. So could you tell me, I've heard of it before, but I don't really know what the advantages or disadvantages are. If someone could, so it's just like a place where all your viewers can hang out together. Is that it, or is there more to it? Am I like, yeah, I'm not 100% familiar with it. So if that's all it is, then yeah, I mean, that sounds great. I'd be happy to do it. Is it a lot of work to set it up? I really don't know anything. So if someone could let me know, that would be fantastic. So let's see. I forgot to. Okay, so I just need to superimpose. I mean, then I'll do it. Why not? I mean, it sounds like fun to me. So. Yeah, I'm just trying to get the background image in. Sorry, it's taking me a minute. Okay, okay, cool. And we have this thing. Okay. Got this. Got this. Okay, I feel like the zoom is going to be slightly, yeah, it's slightly off. Hold on. All right, all right. You guys ready? All that work? Okay, okay. Let me do this so you can see it. Let me zoom down. Okay, so the claim was that this method would work for any implicit equation, no matter how wild, and you should be able to efficiently reflect whatever it is, like 1,000,000 points across the room. We came up with this implicit equation, which is, you know, it's a spicy implicit equation. It's not such a simple one, right? I found this on Stack Overflow, by the way. I'm not like a master of implicit equations, but this should work. And if the theory holds true, okay, it disconnected for a second there. Are you guys still around? Sorry, yeah, it disconnected for a moment, but I think I should be back now. Okay, right at the right at the peak moment too. I was gonna hit play on this animation. Okay. Also, my stream quality has lowered for some reason. I don't know why. Okay, regardless, I'm gonna hit play on this animation now. Hopefully you're all back. All right, let's see. All right, ready, set, go. Off it goes. Look how beautifully it's reflecting across. And I'm telling you, it was no work at all to do this, right? Ooh, there's like weird like shadows coming up. I don't know what those are. But no, this is actually 1,000,000 points. So it just goes to show, if you organize the like logic in your code correctly, you can really get it to work a lot faster. Okay, so I think that's probably going to be it out of me. I had a lot of fun doing that. It was quite beautiful. Let me know if you guys have any other questions. I can probably do like more frames of this animation. It's quite nice, I think. Has a certain charm to it. I don't know. I just really like this stuff. Okay. But okay, no, I really do think that is going to be it out of me today. Now you guys know how to take any implicit curve and like bounce a bunch of points around it. I hope everyone viewing had a great time. Do you think a donut would not be chaotic? I think the theory, so there's like a bunch of unproven conjectures. I'm not an expert in this field, but I can share the code. I'm not really sure. Maybe I'll make a GitHub or something, and I'll put the code up. There's a bunch of like unproven conjectures, and I'm not an expert in this field, but I'm pretty sure the idea is that if it's not a circle and if it's not an ellipse, it's going to probably show chaotic dynamics. I believe that is the theory, but I'm not an expert in it. So don't quote me on any of that. Talk to someone who's an expert in billiard dynamics. But I just make goofy animations, and I just make Homer say "dough" 1,000,000 times. That's my role here. But okay, I'm definitely done now. I hope you guys had a delightful time this Wednesday afternoon. I will edit this down and post it in a couple of days. I hope that I will see you again next Wednesday, and I think that's it out of me. So, peace.